Great, so I'm looking forward to an exciting week. It's my first time in this series as I've been very gradually approaching Feynman integrals that involve elliptic functions. So my thanks to all the organizers for bringing us together online this week. Here I'm going to present work done in collaboration with Samuel Abreu, Claude Dur, Enan Gardi, James Matthew, and my students Ricardo Gonzo and Martijn Hidding. We've been working towards formulating an algebra on Feynman integrals with the structure of a coaction on their diagrams. So we're looking at Feynman integrals as they're typically computed in dimensional regularization as a Laurent series and the dimensional regularization parameter epsilon. So for the simplest Feynman integrals, including all of integrals at one loop, this expansion is given in terms of multiple polylogarithms. And there's a well-known coaction on multiple polylogarithms going back in its earliest forms to work of Goncharov, and then refined by Brown. So based on that, we've conjectured a corresponding coaction on Feynman diagrams, which can be understood in terms of graphical operations. At one loop, we have a pretty good handle on it. There's an integral basis for which the coaction on the multiple polylogarithms is simply related to the graphical operations of pinching and cutting the original diagram. Now at two loops, various new issues arise in trying to formulate such a diagrammatic coaction, including, of course, the first appearance of elliptic functions. And why do this? Well, the coaction is interesting in one respect because it's very naturally compatible with discontinuity operators and differential operators, both of which are heavily used in various ways of evaluating Feynman integrals. So although we haven't outlined the method yet, we hope that understanding this algebraic structure will be potentially useful for computations. So here's just a first example. So I'll explain this all later, but here's just an example of what the diagrammatic coaction will look like. So this delta here, do you see the cursor?
Yeah, we can see that.
Yes, okay. This delta here is the coaction operation. So it maps one diagram onto a linear combination of pairs of diagrams combined with the tensor products. And the first element in each pair is related by contracting or pinching away propagators, right? So here, say this propagator has been pinched away, so the triangle becomes a bubble. And the second element in each of these terms is a generalized cut of the original diagram. So I've just marked some propagators to go on shell. Now the point is that each of these diagrams can be evaluated in DimReg in terms of polylogarithms or multiple polylogarithms in this case. And if we do that, then the coaction on multiple polylogarithms is consistent with this operation on graphs, which I'm just showing this. I'll show the simple examples of the coaction on multiple polylogs. So the discontinuity operator will act on just the first elements in the polylogarithmic coaction, so that's known. So in terms of the graphs, it makes sense that the cut integrals, which are the discontinuities, are appearing in the second elements. That's sort of what's left, what just comes through when you act with discontinuities in the first entry. And likewise, differential operators act just on the second elements. So it leads to differential equations. Okay, so what is a coaction? Time to introduce some mathematical definitions. It's an operation in a bialgebra. So to review, an algebra is a ring with an addition operation under which the elements form a group and multiplication operation with a multiplicative unit, and which is also a vector space over some field. And for us, the field is always the field of rational numbers. That's an algebra. A bialgebra is an algebra with two more maps, of which we're focusing on the coproduct. And there's also something called the co-unit, and they satisfy the following axioms. Since we're very interested in the coproduct, we're going to focus on this one here, which is co-associativity, which means you can apply the coproduct, right? And then you get something in this space, which is a tensor product, H tensor H, and then you can apply a further coproduct on either the second entry or the first entry. And so the two ways of doing that will lead you to the same result. Then there are some other axioms related to the co-unit. Now, okay, that's coproduct. Coaction now generalizes this coproduct to a tensor product of two different spaces. Here's a simple example. I love this example. It's called the incidence algebra. It's a very simple example of a bialgebra, which turns out deeply related to the algebras we come to when looking at Feynman integrals. So let's look. The elements of this incidence algebra are just pairs of subsets of some finite set. So it's like the set of elements labeled 1 through n, and it can have subsets. Those subsets can have subsets in turn. And so a pair will be an element. So to make this a little bit clearer here, instead of writing out all this subset as subset of another set as an element, for short, I'll just take the subset 1, 2, and then I select some further subset to color purple. Right, so instead of this element, I just write it a bit more neatly this way. The empty set is a subset of all sets, so nothing is colored. The empty set is a subset of itself. That's just denoted by a star here. And what are the operations? So multiplication will just be a free operation, and the coproduct is given by this. So coproduct of some element, right? Nested subsets will be a sum of all the ways of inserting subsets that are contained in between S and T. So for example, here are some coproducts in the incidence algebra. So empty set is a subset of 2, and there are 2 subsets in between the empty set and 2, namely the empty set itself here or 2 itself. That gives you 2 terms. Likewise for all the rest. And we can verify that this definition satisfies all the axioms of a bialgebra. So I say, okay, for completeness, I give the co-unit. The co-unit is also very simple in this case. It's just 1 if S equals T, if it's the same subset, 0 otherwise. Now, I think this is the last we'll see of the co-unit. We won't really be using that explicitly. We'll be using the coproduct, or rather the coaction. So it's coming back to the difference now. If H is a Hopf algebra, well, okay, let's just say bialgebra. We don't need a full Hopf algebra. Then an H comodule is another vector space with a map rho satisfying these relations. So this is really the coaction. Rho is the coaction. Delta is the coproduct on the original bialgebra H. So this is just what I was saying before. But you'll have an element. You have 2 distinguished spaces. Anyway, this is a distinction we will mostly gloss over. In this presentation, we continue to use delta for coactions of bialgebras. And the difference between the left and the right space will be very subtle. So now we can directly apply the incidence algebra to a graph. So recall this example from the incidence algebra. So this is the empty set as a subset of a 2-element set. So there are 4 intermediate subsets giving 4 terms. For graphs now, consider just the set of all of a graph's edges. That's it. And we're looking for nested subsets. So if S is a subset of T, then we draw the graph with all edges contracted except for those in T. And of the edges remaining, we distinguish the ones in the smaller subset S by giving them a decoration, which is a mark across the edge. This looks a lot like our first depiction of the incidence algebra. And this equation here, so this is a direct mapping of this equation onto just edges. Right? So I'm not even using the graph structure. It's just really the set of edges. Okay, I'm using the graph structure to show how to contract the edges that aren't being used. And for graphs, the empty graph is just set identically to 0 rather than having an element, which is an empty graph. So this is starting to look like what we can do with Feynman diagrams if we start interpreting these marks as cut propagators. Now we want to evaluate these diagrams and compare them to the coaction on multiple polylogarithms. So let's now review multiple polylogarithms and their coaction. These multiple polylogarithms are described as iterated integrals. Right, so at each step in the iteration, you can introduce a denominator, which is linear in the integration variable. As examples, this includes the logarithm itself, powers of logarithms, classical polylogarithms, and it has a grading by the weight, transcendental weight, which is the number of iterations in this integral. These multiple polylogarithms are closed under multiplication via the shuffle product. So here the summed over the orderings of these parameters, preserving their relative orderings. And here are just a couple examples of the coaction. So there exists a coaction, which in turn, in fact, is graded by weight, which maps the multiple polylogarithms into functions of lower weight in addition to themselves. So here are examples with products of logarithms and classical polylogarithms. Also notably, acting on a transcendental constant, IPi, you get IPi tensor 1. The coaction has become a useful tool for working with multiple polylogs in Feynman integrals. It makes use of the weight grading and it exposes relations among different multiple polylogs, which allows for simplifications. Now, the coaction on multiple polylogs can be written in a form reminiscent of the incidence algebra. We sum over subsets of the parameters appearing in the functions. So the first element in each term has only the subset taken as parameters, so there's less iteration, and the corresponding second element has the full set of parameters here in the list of what you put into the integral, but the integration contour is changed. It's integrated on a contour which encircles this subset of residues in order. Now there's also a coaction for elliptic multiple polylogarithms. This was spelled out in a paper by Britto, Dulac, Pinante, and Tancredi. It would take too long to define everything properly here, and I won't be showing an explicit calculation with it anyway, so I'm just going to summarize the basic idea of the construction. So consider again the multiple polylogs. Another way to approach their coaction is to go through what's called the symbol. Consider the total differential of a multiple polylog. Because of its iterated integral structure, it can be expressed recursively, as seen in this formula. We can then define the symbol, which is an element of a tensor algebra whose entries are rational or algebraic functions. Here, so we just kind of take off the differentials, put in a tensor product, and construct something like that iteratively. Now this symbol can be understood as the maximal iteration of the coaction. So after constructing a symbol, we can work on lifting it to a coaction, which is a more powerful tool than the symbol, although both have been very useful. So these people try the same approach for elliptic multiple polylogs. Now, what are elliptic multiple polylogs? There are a few different versions of this kind of concept with different pros and cons, but this is the one that leads to the coaction that we're studying and using. So here, this is also defined by an iterated integral, but now you see there are a lot more parameters involved, and these integration kernels here, these come from, so tau is taken from an elliptic curve, and the kernels then are constructed through a generating function, which is constructed from Jacobi theta functions. So this definition as iterated integrals, I should say, the other definitions are also various kinds of, there's another version which is iterated integral. So perhaps something similar could be done, but for us, this is sufficient. This iterated integral structure leads similarly to a recursive total differential formula. Just copied here. There are a lot more definitions involved, but this is just to show that there is a similar kind of formula, these omegas are differential one forms, which are fixed. So this leads similarly to the definition of a symbol and then eventually a coaction after many, many more definitions. And I refer you to the paper by Britto, Dulat, Panente, and Tancredi for the extensive details. Okay, now we'd like to see how we can use this in diagrams. So the first step is to take a good look at one loop integrals. So several years ago, we proposed the one loop diagrammatic coaction, which is this idea that the coaction on one loop graphs, or rather a basis of one loop graphs, which can be defined by just pinching and cutting the graphs, subsets of propagators, when evaluated by Feynman rules in dimensional regularization and then expanded order by order in epsilon, the proposal is that that will agree with the coaction, the known coaction on multiple polylogs. Now, in order to interpret diagrams as integrals, we need a little bit more information. At one loop, we take them as scalar integrals, right? So if I just give you a picture like this, you can say, okay, it's one loop, but how exactly do I construct the integral? We take them as scalar integrals, and we have to know in which dimension we're evaluating them. So based on the number of propagators, we choose the dimension, according to this formula, whether n is even or odd, so it's always in an even number of dimensions, minus 2 epsilon. And this basis is nice because it does give a basis of one loop integrals, and the functions are pure when normalized by the leading singularity. The very simplest example we could look at then is the tadpole, or the very simplest one loop integral. So this, according to the formula on the previous page, this should be evaluated in 2 minus 2 epsilon dimensions. We then write this formula from the incidence algebra. Right, so this is just an operation on graphs. The idea is whatever is not pinched, whatever propagators are still visible here, will be cut in the second entry. So there's just one propagator. If you pinch it away, there's nothing. So there's only one term with that visible. And then because that's still there, it has to be cut here. Okay, so we know what the tadpole integral is in 2 minus 2 epsilon dimensions. We also know what its maximal cut is. It's easy to evaluate in any number of ways. And it's also, so given these formulas, it's easy to verify that the epsilon expansion is consistent with the coproduct on logarithms. For more complicated examples, we'll need to define our cuts very carefully. And in fact, for the diagrams, we'll find a specific modification that we need to make to the naive construction from the incidence algebra. But first, I'd like to talk about how to define cuts. So we define generalized cuts as residues. Instead of putting delta functions into the integrand to put propagators on shell, we're going to change the integration contour to encircle the poles of the cut propagators. This resembles the contour modification that we saw for multiple polylogs. We evaluate the cut integrals only modulo I pi. This is enough to be able to use them in the second entries of the coaction, which is where they appear, because the coaction for multiple polylogs is also, well, it's on the space of multiple polylogs taken modulo I pi. So this is coming back to this, for us, rather subtle point about the distinction between the coproduct and the coaction. One way to think about them as separate spaces is understanding that the uncut, or that the second entries can be interpreted only as cut integrals, or in terms of the polylogarithmic coaction, that they have to be taken modulo I pi. And this is related to that formula that the coaction of I pi is I pi tensor 1. So this freedom then also allows us, when we're doing this, to choose convenient and independent integration regions. So we're not too bothered about the details of the kinematic regions. Cut integrals can be understood as discontinuities. We can see this precisely in the framework of homology theory, which has other applications that are useful for us here. So the proper definition of cuts, we can invoke homology theory to understand the integration contours. And this leads to relations among the various cuts. So here we understand that the kinds of residues that are appearing in the integrals are Leray residues. A Leray residue is defined as follows. If you have a differential form here and you're looking for a residue around s equals 0, then you try to decompose your differential form such that you see a ds over s appearing, and then together with some other forms that are regular on that singularity. And then you read off the residue as this coefficient, if you will, psi restricted to the singular space. Applied to cut integrals, so we're taking residues at a singular locus. It's the locus where the propagators are going on shell, the kinematic space where those on shell conditions are satisfied. And so the equations shown here at the bottom show that the Leray residue of the integrand can be recast by Stokes' theorem as an integral of the original integrand over a contour encircling the pole, a tubular neighborhood. Now, if we think of all generalized cuts and all the ways to construct these contours encircling poles, we're confronted with the existence of a pole at infinity and its residue. Now, at one loop, there's a powerful theorem from homology which shows that it's enough to consider the cuts of visible propagators. That's this decomposition. So here, a contour encircling the pole at infinity turns out, this is just the result of the theorem, that it's a linear combination of these other contours, the one without infinity with some free factor, and then all the other ones summed over C as rather X propagators, a set of propagators that include all the cut propagators. And there's a difference here appearing depending on whether the number of cut propagators is even or odd. So thinking ahead beyond one loop, we know that this geometry, this homology analysis is going to get very complicated because of the geometry of multi-loop integration. But it turns out we can still largely rely on the one loop results when we integrate one loop at a time. So let's return to the simple one loop examples. Moving on to the next example, which is the bubble. The diagrammatic formula that turns out to be correct is the naive one. Well, the naive one is this, right? We just have all the pinched diagrams here and then the corresponding cuts here. But there are some extra terms that we call deformation terms, which are the last ones here in the parentheses. Now, to understand where these are coming from, I've rewritten this exact same equation in terms of integrals here. This is just shorthand. So now this omega just means the integrand with propagators 1 and 2. And the contours are also labeled by which propagators are being cut. Right, so here nothing is being cut, this gamma empty set. Okay, so I've just rewritten everything in integral form. And now by combining these combinations, right, so these cuts are just different contours. We can also combine the contours linearly. Now it turns out from that decomposition theorem, okay, so what's missing here is just this third line. It's very similar. This is not an infinite series, just a slight shortage of space. But we can see here, by combining this contour with this contour, we get exactly this combination, which is just the contour related to 1 and the pole at infinity. And now, see, now we even have space to bring in this extra term. The last term is just this combination, which is a contour related to the pole at propagator 2 and infinity. And then it just happens to be mapped back to this additional cut here. Okay, so this is the same formula from the previous page. So we have a basis now of integrands and corresponding contours. So now we can see, instead of this being puzzled about where these terms are arising from, we understand exactly how to pair the terms in this coaction. When you have the propagators that are not being pinched away, then in the second entry you encircle those residues, right? So you cut those. But if it's an odd number of edges, then you add infinity. And this distinction between odd and even was exactly the one that was already visible in the decomposition theorem. It comes from understanding homology properly. So this is the only modification we need to make. And we believe that this pattern holds for all one loop integrals in generic kinematics. And then you can take massless or equal mass limits as desired carefully. And we've checked many examples of those. There's another comment about these pairs of integrands and contours is that at leading order and epsilon, they are dual in a way that can be expressed at this condition, that at leading order and epsilon, this matrix is the identity. The diagrammatic operation can also be applied to cut integrals. If a propagator is both cut and pinched, then the whole diagram is set to 0. So you're just left with whatever you're left. So in fact, you can just apply cuts to the previous formulas. Like you can take this here and, so I'm just showing the maximal cut of a triangle, but coming back here, if you were to say to cut both propagators, that would just leave you with this term because here you're trying to cut something that's already been pinched. So this would be 0, this would be 0. And that would leave you with a group-like formula. So the maximal cuts are group-like in this sense, that their coaction just gives the same thing times itself. So to summarize what we find beyond one loop, we have some examples of a similar structure, which I'm coming to. Since it's harder to understand the geometry and perform the computations, we do not yet have a general prediction, but we are working towards formulating one. And this we're heavily inspired by Brown's motivic Galois coaction on Feynman integrals. Now, of course, given the subject of this week's workshop, we're especially interested in the appearance of elliptic integrals. But now, before we look at the two-loop examples, let's just review the general framework. As we're looking for coactions on various integrals, we're looking for this type of integral formula. Right, so the first entries in the coaction have different integrands, and the second entries have different contours. So this is a lot like just inserting a complete set of states, some kind of basis here. And this formula is meant to be applied compatibly to Feynman integrals with cuts. So that's like what I was just showing for the bubble. Also for multiple polylogs and elliptic multiple polylogs in the epsilon expansion. So that's like the illustration of choosing different contours there. That's the same kind of formula also applies. And finally, also for unexpanded hypergeometric functions using intersection numbers. So without expanding an epsilon, Feynman integrals can be expressed as generalized hypergeometric functions. We found in some cases that it's possible to construct a coaction on hypergeometric functions directly that's consistent with its expansion in multiple polylogs. We have some preliminary results and are pursuing that further, but I won't discuss that here. And again, I remark that the coaction on integrals resembles the incidence algebra. All right, so at two loops, what we have are some examples. Let's start with some examples that are still polylogarithmic. So here's the sunrise with one massive propagator. Now at two loops, we have a new feature, which is that you can have multiple master integrals appearing in the top topology, and they must be considered together. So here, for this sunrise with one massive propagator, let's choose this basis. These integrals with the prefactors given here are pure in 2 minus 2 epsilon dimensions. Typically, when you're thinking about the sunrise, you might take the second master integral to be one with a squared propagator, but here we've written one that has a numerator instead. They both have a closed form expression in terms of the Gauss hypergeometric function 2f1. So we can compute the coaction. We can do this to all orders, actually even with for 2f1, and we find the following equations. Well, so what I'm showing here, I'm just showing the pictures now, but you can actually do this to the multiple polylogs and the expansions, and the point is that these diagrammatic equations will be true when mapped to the multiple polylogs if everything is defined properly. So let's make some points here. So notice that now both master integrals, right, for a given master integral, its coaction will involve terms with both of the master integrals appearing in the first entry. They're being mixed. This makes sense when we think of the differential operators acting on the last entry, because both the masters satisfy the same differential equation. It's a coupled system, so we're happy to be seeing both. That's what should happen. In this example, now there are nothing is being pinched in the first entry, right? Everything has the same shape. This is just an accident of this example, because you can imagine pinching a propagator, but then you'd be left with a double tadpole. And now because two of the propagators are massless, and massless tadpoles are 0 in dimreg, there is nothing that's non-zero that you can still write down here. So that's why this is quite simple here. Now, corresponding to the two masters in the top topology, the space of cuts, actually all cuts, has dimension 2 as well. And there are two solutions to the maximal cut equations. So while we could consider other generalized cuts and try to feed them into this equation, it's not necessary because there are linear combinations of these. And in fact, we prefer here to take for our basis two independent maximal cuts, because that allows us to continue the same pattern we observed at one loop, where diagrammatically, wherever a propagator appears that's not being pinched, that same propagator is in some sense being cut in the second entry. So now, just as at one loop, we need to understand precisely how to compute all these cuts. So let me just show a bit about the two maximal cuts. This is showing how we set up the cut calculation. So we integrate one loop at a time. The order shouldn't matter, certainly for a maximal cut, but for other ones, you also might want to check the order doesn't matter. So the first loop here is a familiar one loop calculation, maximal cut of the bubble. We know how to do that with our definitions. After that, then we still set up another integral where we have to take one more residue of a propagator. Now this residue isn't enough to completely fix the integral. There's still some freedom left in choosing an integration contour over the last integration parameter. So here, right, I haven't specified the contour. We can choose the endpoints of integration from among the branch points of the integrand. So we've got three factors here. There's also a branch point at infinity, along with the zeros. And the possible choices give two independent results. If you recall the Euler integral formula for Gauss hypergeometric function 2f1, you'll recognize that here. This is a 2f1, as expected. So this is the same analysis then of integrating between branch points that's used by Aomoto to generalize the notion of hypergeometric functions. Anyway, so here it's consistent with 2f1. We get two independent integrals. And here in computing cuts, we're also still always working modulo I pi. Okay, so then coming back, so we just choose to define 1 and 2. Actually, the best we could say at this point is that we choose the two independent contours such that this formula works and that there exists a choice of basis of the maximal cuts such that this is exact and compatible with a coaction on multiple polylogs. Here's another example. This is also expressible in terms of 2f1 function. So this diagonal box has only one master integral in the top topology. But now, so that's this. Now we do have some pinched integrals appearing. You can pinch away a propagator and be left with something, and they appear together with their corresponding cuts. And the cuts here are straightforward to evaluate. And the formula looks very much like the one loop examples, again, in the sense that the propagators that are still appearing on the left are being cut on the right. A more complicated example is still polylogarithmic, but now we come to the sunrise with two massive propagators. So I've just drawn our result very schematically here. We computed it, although you can't see from the diagram, we did compute it for two distinct masses, M1 and M2 here. So here again, there, just like in the diagonal box, there is a pinched integral, right? So here's the easy part. And the different colors of cuts represent sort of different solutions to the maximal cuts. Okay, but here there's a pinched integral because there now is a non-vanishing double tadpole. And it comes along with what you'd expect, the integral where you'd cut the two massive lines, but also these deformation terms. The deformation terms appear here, just like at one loop where you cut an extra propagator. And so the way we understand this is that these deformation terms are directly inherited from the one loop structure. As you're integrating loop by loop, you consider what the pole at infinity is doing. You map it back to the visible propagators in that loop and keep going. So we've found sort of a choice of the maximal cuts and this cut that make this correct. And for completeness, here's also the coaction on the fourth master integral, the double tadpole, which of course follows from the coaction on one loop tadpoles. Here also we were able to use the hypergeometric coaction on appel F4 to compute these in closed form, or to all orders in epsilon, if you like. So a remark I'd like to make is that pinching propagators in the first entry is not going to reduce the loop order. So we're always still going to get two loop integrals in the first entry if we have a diagrammatic coaction. This is in contrast to Brown's motivic coaction where the loop order was reduced. But we don't expect to reduce the loop order. We don't expect to be able to because of the relations with differential equations. All the master integrals are solutions to the same differential equation, so they come with the same, and they come with the same loop order. All right, so now what about the elliptic case? The calculations get very heavy, of course, so we're going to start by looking at the elliptic sunrise, starting with the equal mass case. Now, to assemble a coaction, we must compute the cuts, and we have the same kind of freedom in defining cut contours. These cuts can be obtained by direct integration or by a method involving differential equations, which we've used primarily. This uses this package by Martin Hitting, which he will discuss more on Friday, called diffexp, to transport boundary conditions to convenient kinematic points. So we used a Bykov parameterization and the canonical basis given by Adams and Weinzierl. Here's the basis and the differential equation for the equal mass case. Now in the differential equations, this method of computing cuts, we compute boundary conditions for each of the cuts at some preferred kinematic point. So just find some limiting case in which the integral really simplifies, and you can write it down nicely. And then with great care, you analytically continue to the even more special point x equals 0, where the expansions in epsilon then are observed to evaluate to polylogarithmic constants. Then you can solve the differential equations in terms of iterated integrals of modular forms and continue back to whatever point you like. So here we have actually found a coaction for the elliptic sunrise in the equal mass case, where the master integrals appear in the first entries and cuts appear in the second entries, and which is consistent with a coaction on the elliptical multiple polylogarithms that appear. So that's one of the elements we're looking for that really gets us on the right track. What we have not quite got yet is a diagrammatic version where you have really nice picture where you have the uncut propagators in the first entry, the visible propagators in the first entry corresponding to the cuts in the second entry. And it's not that it's impossible, it's that actually that we have this mess of prefactors and change of basis. So actually we hope to get this into a diagrammatic form very soon. I don't really see an obstacle, but are not quite there yet. Also in progress simultaneously is the case, the unequal mass case. It's not tremendously different. It's a heavier calculation. We have 7 masters, of course, if you in that case, but I have a similar procedure, and we will be looking to that for guidance too, because if the masses are distinct, then you could consider limits to the 1 mass case and the 2 mass case, which we do understand diagrammatically. to organize and to see if there are deformation terms that appear. Because we also know from our experience at one loop that if you take many masses to be equal, it's just harder to see the pattern, right? If too many variables are the same, you can get some coincidences. So we're still working on that and are very excited to see what we're going to find soon. Let me then close with that. That's where we are. So to summarize, we do observe in many examples a coaction structure on Feynman diagrams. At one loop, there's a basis for which the coaction is simply related to pinches and cuts of the original diagram. And a similar structure is emerging in two loop examples. The elliptic case is being explored through the sunrise example primarily. There is a coaction involving cut integrals that's visible in the equal mass case. The diagrammatic version of the unequal mass case are still in progress. So the diagrammatic coaction corresponds to the coaction on multiple polylogs or elliptical multiple polylogs in the epsilon expansion. It's important, of course, to understand what the cuts are. They're constructed as residues with final integrations taken between branch points of the integrands. That means certainly going beyond one loop, it's not enough to say which propagators are being cut, right? Because you also have to describe, on top of that, which contour you want to take in which case. The coaction has deep connections to discontinuities and differential equations, which we hope will lead to better tools for computation. And then the final point is just that we have this sort of unified vision of the formula for a coaction, the coaction on integrals, which looks a lot like an incidence algebra, which is based on matched pairs of integrands and contours, which we conjecture to be applicable to generalized hypergeometric functions that appear in Feynman integrals as well, which is another direction for exploration, especially in the elliptic or non-polylogarithmic case in general. Thank you.
All right, thank you, Ruth. We can try for a real applause here if people want to unmute themselves quickly. And then, if people have questions for Ruth, we've got a couple minutes because I took up the first couple minutes of the talk. But while we're waiting for more questions to come in, I guess I'm wondering if you had the diagrammatic coaction working at two loops right now, what would be the first place you're interested in applying it?
Good question. I mean, it's hard to, I guess we would hope then to be able to understand it, I mean, to all loops right away, right? Many of these features that appear at two, I mean, just the fact of having multiple masters, for example, or having something non-polylogarithmic, or having to make the move to hypergeometric functions, I think would at least allow us to propose some coactions for higher loop orders as well, or even non-elliptic cases, where then we might not even have a coaction on the function. And okay, so then, yeah, if you could do that really diagrammatically, that might then also give some clues into how to set up differential equations.
Okay, yeah, thank you. We also have a question from Niels.
Hi, Ruth. Thanks for a great talk. So I think this is just my confusion, but so if I understand it correctly, you want a coaction on the Feynman diagrams, but it seemed to me that you construct it by looking at the Feynman integrals. Is that correct?
Yes, well, you could say, I mean, naively, when I just first showed the illustration of the incidence algebra, you set it up on diagrams, but it, of course, doesn't mean anything physically until you say what you want it to do on Feynman integrals, and then you find you need these deformation terms.
Okay, so
let me emphasize, though, that actually introducing the deformation terms actually doesn't really change the fact that it's an incidence algebra. It's an algebra isomorphism.
Okay, so the point is that the coaction on the level of Feynman diagrams is really just a special case of an incidence coaction. Is that what you're saying?
Yes, and of course, yeah. I mean, to see which version it is, you would have to understand something about the physics. So, right, I mean, you can do this purely on graphs with no physical input, and of course that's, I mean, then you're done, right? That's not very illuminating.
Okay, so the game is then
Okay, the point,
related to
yeah, I
the
mean, that it
integrals.
is based on this combinatorial structure.
Okay.
But the point is that then this can be, there's a mapping of the combinatorial structure into something that's physically meaningful in terms of the functions.
And you want that coaction on one side to be compatible with the one on the other, of
Yes,
course.
yes.
Okay, thank you very much. That was helpful.
Okay, any other burning questions out there? If not, we've got the Slack channel, and also we'll have the discussion tomorrow. I don't see any other hands raised, so let's give.
May I ask a question? I can actually not raise my hand as I co-host.
Yes, go for it.
Thanks for the interesting talk. So just maybe a more technical question on the example with the two mass sunrise. No, okay, it was the one mass one. It looked very symmetric in the two contours. That was on the page 17. Was that a generic feature or just an accident because of the simpleness of that example?
Symmetric, you mean that there are, yeah, I mean, if there were, I mean, there could be prefactors that are absorbed into the definition of the fact, into the cut. But no, actually, I think so these are just two maximal cuts. I mean, I'm sure that there isn't really a symmetry here because, of course, these two masters are quite different, right? One has a numerator and the other doesn't. So it's.
But
So it's just true. So I mean, the point is that each of those masters has its corresponding contour. And yeah, so it's beyond that. No, okay. So yes, and it does work out nicely, of course, that these sort of cross terms don't have any additional factors. I can't say it's due to symmetry. No, so that goes. I guess that just goes back to this kind of formula. There is some kind of basis or two dual bases. So once you have identified a basis and then its dual basis, then this kind of structure does give a coaction.
Okay, thank you.
Okay, thanks again.
All right, let's thank Ruth again, and then we will move on to Roman. Great.